Good afternoon, folks. How's it going? Mike coming back at you with another video on Precalculus. In the previous video, we talked about modeling it using variation, more word problems coming back at you, where we had to interpret those words to come up with the correct variation model and then solve the given problem. In this video, we're going to start a new chapter. We're going to begin talking about a different kind of function compared to the previous chapter. We are going to talk about exponential functions. But what are exponential functions? An exponential function is of the form f of x equals b raised to the power x, where b is a positive number that's not equal to 1, and x is any real number whatsoever. This is actually not the most general form of exponential function. The most general form would actually be this right here. F of x is equal to c times b to the x. And c here would actually be f of 0. Whatever you know the value of the function to be when x is equal to 0, that is what that constant out front is going to be. Here are some examples of some exponential functions. They either shoot up at a very, very fast rate as x increases, or it decreases very, very fast as x increases. And based on what our base is, that will dictate which one this thing is doing. If our base b is greater than 1, then as x increases, our curve will shoot up very fast. If our base is between 0 and 1, then our curve is going to go down at a very fast rate. Some properties of the exponential function. We definitely want to talk about these guys. The exponential function has all real numbers in its domain. Any x value whatsoever, that is something we can plug into the exponential function. The range is all positive real numbers, any number strictly greater than 0. There is no x intercept. The exponential function never ever touches the x-axis. However, there is a y intercept, and no matter what our base is, the y-intercept is going to be at height 1. So the point 0, 1 is going to be on the graph of every exponential function. 3. The exponential function is 1-to-1 and thus has an inverse. Very shortly, we will be getting onto what does the phrase 1-to-1 mean. In fact, we're going to be coming up on it so quickly that here it is. What does 1-to-1 mean? A function is 1-to-1 if distinct inputs yields distinct outputs. That is to say, if you take any two different x values and plug them into your function f of x, if your function is 1-to-1, then you will get different y values out, or you'll get different outputs. Graphically, we can tell a function is 1-to-1 or not if it passes the horizontal line test. So what we are doing there is we are either visually imagining horizontal lines or physically drawing horizontal lines through the graph of our function. If every single horizontal line intersects the graph of the function in at most 1 point, then your function is 1-to-1. We can look at this here. Let's draw some horizontal lines anywhere through this exponential function right here. Can go up, go down, wherever. Every one of these lines is only going to intersect that red curve in at most 1 point. Same type of thing for the blue here. Draw these horizontal lines anywhere. Again, it's only going to intersect at 1 point each. So that's how we know that our function is 1 to 1. If the base is a positive number that's less than 1, then the exponential function is decreasing. If our base is greater than 1, then the function is increasing. And the exponential function does have a horizontal asymptote. The horizontal asymptote is going to be the x-axis. Now, just by looking at a set of points, how can we identify if we have an exponential function? The way that you identify an exponential function is that if you look at consecutive outputs of points, an exponential function will have a common ratio. So here's an example as to what we are talking about. I have an x value and then a corresponding y value, and I have 6 points here. If I were to take the quotient of the larger x and y value divided by the smaller x and y value. If I look at the y values and I did this guy divided by this guy, you would find that you would get the ratio or quotient of a positive 3. Now, if this truly was an exponential function, which it is, we can do the same thing for other pairs of consecutive points. If I do 4 divided by 4/3, that gives me 3. If I do 12 divided by 4, that gives me 3. And you can verify the other ones. 36 over 12 is 3, and 108 over 36 is 3 as well. Whatever that common ratio is, in this case 3, that is going to be your b value. That is going to be the base of your exponential function. So in this case, it's going to be something involving a 3 to the x. At the beginning of the video, we said that the general form was c times b to the x, where c was the value of the function at x is equal to 0. So here, when x is 0, y is equal to 4. So we can write the actual formula for this exponential function. It's going to be 4 times 3 raised to the power x. But big thing to know is exponential functions have common ratio between consecutive outputs, and then whatever the function's value is at 0, that is the constant that goes out front here. Just as a quick recap, quick little thing to mention, some common transformations we can do with the graph of the exponential. If I have x raised to the power b, if I have the function b raised to the power x minus c, then this is going to be a horizontal shift. If c is positive, then this is going to shift it right. If c is negative, then this is going to shift it left. We can do a vertical shift, up or down. To do that, we add a constant onto the end of the function. So b to the power x and then plus c. If c is positive, that shifts it up. If c is negative, that shifts it down. And multiplication by a minus sign, depending on where it is a reflection of some kind. If I multiply the entire function by -1, that reflects it over the y-axis. If I multiply the variable by -1, then that reflects it over the x-axis. Now, there are plenty of exponential functions out there in the world that we can use, but there is one that we use more than any other one. This is called the natural exponential function. It's the function e raised to the power x. E is a real number, rounded to 5 decimal places. It's 2.71828. and there are many applications of this function in the real world. I'm going to introduce you to one later on in this video, and we're going to be doing some real world applications with this later on in this chapter. But before I give you an example in this video, I just want to quickly refresh you guys and restate the properties of exponents. These are all things that you should be familiar with. This really shouldn't be anything crazy here. If we are taking the product of two things that have the same base, then we add their exponents. That's what number one is saying. A to the b times a to the c is equal to a raised to the power b plus c. Similarly, if we're taking the quotient of two things that have the same base, then we subtract their powers. A to the b divided by a to the c is equal to a to the power b minus c. Third, if we're going to take something that's raised to a power and then raise that whole thing to some other power, then that's the same thing as multiplying those powers. So a to the b, all raised to the c, is equal to a raised to the power b times c. 4, for any root that we take whatsoever, could be square root, cube root, fourth root, sixth root, 10th root, whatever. The nth root of the product of two things is equal to the product of the nth roots, and the nth root of the quotient is equal to the quotient of the nth roots. How can we rewrite the nth root as a fractional power? The nth root of a is the same thing as a raised to the power 1 over n. And then using that in combination with number 3 here, the nth root of a, that whole thing raised to the power b, is equal to a raised to the power b over n, and that's the same thing as the nth root of a raised to the power b. So those are just the main properties of exponents that you want to keep in mind. Now, our application of that natural exponential function. Simple versus compound interest. This is a classic example that you see fairly often. So suppose you have $P to invest or to deposit at an annual interest rate R that's compounded n times per year. So if you compound or calculate interest n times per year over the course of t years, there will be nt time periods, nt number of times that you have compounded or calculated interest. Well, simple interest, after every time period, the interest you get on the $P that you put in at the start is P times R over N. Now, as a note, this annual interest rate R, this is being used as a decimal, not as a percentage. So if your annual interest rate was, say, 3%, you're using it here as 0.03, not 3. And every time that interest is compounded, you are getting the same quantity of interest being added into your account. So what's really happening here is with simple interest, the interest you're getting every time period is only based on how much money you put in at the start. Compound interest, whenever the first time period hits that interest is calculated, the interest you're getting is P times R over N, which makes your balance at the first time period P times the quantity, 1 plus R over N. When the second time period hits, you're getting the interest of P times 1 plus R over N times R over N. We have that same factor of R over N, but now it's on the balance that you had at the end of your first time period, not just on what you put in at the start. This is saying the same thing as making your balance P times 1 plus R over N raised to the power 2. And we keep going on in this same method. After the kth time period, the interest you get for that time period is given right here, and then that makes your balance this guy right here. P times 1 plus r over n raised to the power k. So what happens in compound interest is you're earning interest based off of your previous time period balance, not what you put into your account at the start. So the general formula, if you compound interest n times per year on p dollars at an annual interest rate r, after t years, this is going to be your account balance right here. P times 1 plus r over n raised to the power nt. Well, as we compound interest more and more often, like every tiny fraction of a second, like every millionth of a second, billionth, trillionth, the number of times that we're compounding interest is increasing without bound. That's to say, n is going to positive infinity, and that formula becomes the famous continuously compounded interest formula. A equals P times e raised to the power RT. Later on in this chapter, we're going to do some sample problems, and we're going to see how we can use that formula. So this concludes our discussion of exponential functions, its properties, some common transformations, and the properties of exponents. In the next video, we are going to begin to talk about a related type of function, namely the logarithmic function, and we're going to see how the exponential and logarithmic functions are related to each other. Guys, if you have any questions or comments, please be sure to reach out to me. Emails, texts, phone calls, knocks on my door, rocks through my window, whatever you have to do. Until the next video, take it easy.